Hello, I'm Kazım Kıvançeren. I am a machine learning engineer at Ideal Technology Solutions, and I am a PhD student in computer engineering at Kocaeli University also. Now, I'm going to talk about the development steps of a system that estimates early stage efforts of different kind of software developments based on machine learning by taking advantage of customer requests. Before I start, I have to mention our paper is in collaboration with researchers whose are Ayşe Tosun and Beyza Ken from Istanbul Technical University. One of the main challenges of software organizations is to estimate how much time it takes for solving an issue. This issue can be bug fixing or additional software development process which comes from customer needs. In many organizations, expert judgment is still one of the most popular behavior to estimate software efforts. But the main problem, this solution may be misleading in cases when the expert is not accustomed to the new project, and this may be caused to make erroneous estimations. Also, making correct predictions about effort is important for prioritization. If you have more than one development to do, it's important to know correctly how long this development takes. Another important issue is the customer wants to know how long a development will take. Whether the time is long or short to complete this job may change the customer's idea. So the time spent until effort is determined is also important. The figure shows the steps from creating a ticket to assigning it to the software developer in our company. First, customers create a ticket related to their request. They can create these tickets directly through a system or by calling our company's support team. In this case, the support team creates the ticket instead of them. If the support team can solve the ticket-related issue, it solves the issue after performing a pre-analysis step. But the problem is more complex. It needs to be analyzed by an analyst. So analyst makes an analysis and creates analysis document and sent to tester to determine testing cases for the approval of the solution. After that, a software leader who receives the analysis document and test cases, it predicts the effort required for this development process and create an RFC record. RFC is request for changing, which indicates that an additional development is needed here. At the CAP meeting, team leaders and project managers come together to decide whether this work will be done or not. If this request is accepted, task appointed to developer. If rejected, this development is suspended to be done later. As can be seen, until CAP meeting, there is a lot of process to predict effort of software requirement. And end of the day, if it's decided not to make this development, it's obvious the time spent will create an additional cost for the companies. So the aim of the paper is to propose an early stage effort estimation model that can be predict the effort of a software development process as soon as the ticket is created. We believe customer requests are important. We thought the complexity of a job is related with what customers want. So the complexity of customer requests affects the effort. Customer requests in text format can contain meaningful information for predicting effort. If we can find this meaningful information, it can be useful for estimating the effort. So for this purpose, we have collected data from our system, which contains 1,648 complete software development tasks from 7 different companies or 2 consecutive years. In the figure on the left, the number of requests came from companies is very different for each. The reasons for this can be such as some customers may use more than one software product. This increases the number of applications that can receive possible errors. Some customers may be less active about to use products, maybe not prefer to use in daily jobs, or some of them use low version of software products, so they take advantage of less features, so it indicates lower possibility to encounter with errors. The other figure shows effort distributions for our data set. Our aim to predict these effort values. As you can see, most of effort values are between 0 to 400 man-minutes. When we looked to the data set, we found that customer requests are generally about some certain kind of issues, and those issues usually are not major, but only a little part of issues are major. So that could be a main reason of why effort values intervals are like that. Our raw data consists of 7 different attributes. Our aim is predict the effort. The effort values are the summation of efforts that is from start of analysis to end of the development process. So effort values contains the total time spent during the whole process, which are analysis, test, and development efforts. For other attributes, we categorize 2 groups. These are non-textual features and textual features. We use these features as our effort estimation inputs. For non-textual features, we don't need complex pre-processing, but we had to apply some simple pre-processing steps. There is what we have done about this. Customer type is nominal feature that contains customers' names such as customer 1, customer 2, and so on. This feature shows which customer made the request. We use this feature as a feature in our unified model, which is a general model that predicts effort for all customers. And we used these features to split the data set to little sub data sets. This contain only data for individual customer, and we after that use these sub data sets to build models for each individual customer. A ticket related to a customer request can be created by our support teams or by the customer itself, as we discussed before. The request type field stores this information. We think there is a difference between the ticket created by a customer or our employee. When the support team creates the request, solution may be faster because the employee is actively involved in that request directly. Application type stores application and customer pair. For example, company 1 Android, company 2 web service, etc. We mapped into just platform names as web service, and mobile. And month, we believe seasonal information could be effect of employee motivation. For example, maybe in summer, the employee thinks to make a good vacation and their patience to work will decrease. The other feature group is the textual features. We believed customer descriptions gives a good information what is the complexity of a work. So we applied a pre-processing step for extracting meaningful information from customer description. We use K-grams for extracting useful information from customer requests. Before we start what we have done, we have to explain about some details of our scope. Firstly, our description texts are in Turkish because our company residence in Turkey. So our customers are Turkish companies. Turkish is an inflected language, so a root of word can inflected from many different combinations of morphemes. When we look at the figure above, this is different inflection form of add button in Turkish buton ekle. But actually these inflections indicate actually same things, same meanings. So if we take expressions with the same meaning as separate features, this will lead to sparsity, and this can be cause overfilling. So we wanted to avoid them. We merged this feature as one feature. The left side is our flow when we extract textual features. We applied tokenization for each customer descriptions. This tokenization based on the sentence, we divide each sentence and also by punctuation marks. After that, we find prefixes of each tokens, but prefixes should larger than 3 characters. If less than 3, basically we dropped, because most of Turkish root starts from 3 characters. Less than 3 is generally as stop words. At top of the right, we extracted different prefixes which are unigrams also, because just only one word. We counted number of documents this word passed, and also how many times passed in these documents. After collected this information, we can find smallest and common representations of words. If you look at the first 2 words, if 2 words, but and buto, passed in the same number of documents with same frequency. So but is only the root of buto, and it can't be the root of another word. So buto word can be represented as but. So we basically drop buto word. And this situation is also valid for this and this. The figure at below shows the final result. We think that the use of word groups is also informative as singular words. We applied same approach on binary word groups. In our case, binary word groups are the combination of prefixes, as can be seen as the figure above. When they are in the same number of documents and have the same frequency, we take the simplest ones. The simplest one is taken, as we did at singular words. End of this process, 17,186 features are obtained. In our experiment, 5 data sets are created. The first one, non-textual data set. It contains only non-textual features before we have talked. Frequency feature extraction. Frequency means how many times a kgrams occurs in current customer request description. We basically count how many times this kgram occur in a description. After that, we applied linear forward selection to reduce this feature space. Next one, binary feature extraction. Binary values indicates related kgram is occurred in current description or not occurred. For each customer request, we basically check are kgrams occurred in text or not. One shows kgram is observed in the description, 0 is not observed. Also, we applied linear forward selection on this. Non-textual and kgrams frequency, we merged their non-textual feature with frequency kgrams. NKB, non-textual and kgrams binary, indicates non-textual and binary kgrams data set are merged. For each data set, we trained 4 different models: card, classification, and regression trees. Analogy base, which is similar to KNN, you find nearest requests of your current request and make prediction by looking at these neighbors, for example, mean effort of neighbors. Linear regression and random forest. We also evaluate our models with 3 different validation techniques, which are leave one out cross-validation, 5-fold, and 10-fold cross-validation. We built 2 models. For unified model, we used all data from each customer. But customer-specific models trained only with the data of individual customer, and we are gonna use to predict the related customers' requests. We evaluate our models with 3 different metrics. The PRED, which reports the percentage of estimates that are within X% bound of the actual value. Standard accuracy is based on the mean absolute residue, aka mean absolute error, that measures how much a predictor can be better than random guessing. Where MAR-PI is defined as MAR of effort estimation model PI, and MAR-P0 is the mean value of typically 1,000 times run random guessing strategy. For random guessing strategy, the effort value of a randomly selected sample from the dataset is considered as the prediction result. We also used Gibbs delta, which shows about how much better our prediction model than random guessing, where STP0 is the sample standard deviation of the random guessing. The delta values is exactly equivalent to z-score of normal distribution, and the delta value can be interpreted as how much the MAR PI value of effort estimated PI different from the mean of random guessing error distribution. Our expectation for good model is high value of PRED, high value of standard accuracy, and also high absolute value of Gibbs delta. At figure below, we summarize best results for these data sets. For unified model, when we used features alone, without merging, if you compare for higher values of PRED and standard accuracy, and also higher absolute value of Gibbs delta, it can be seen non-textual data set gives better prediction results than binary and frequency feature extraction techniques. For same comparison for k-grams, you can see at figure frequency feature extraction, the last one, is better than binary k-grams, the second one. We can say how many times a k-gram occurs in the relevant text is more informative than just to look if the word exists or not. Among the data sets, as you can see, random forest with 10 cross-fault validation gives us the best prediction results. But in our results, also we observed that the analogy base gives closest results to random forest model. Merging non-textual features with k-grams increase the prediction quality. The best two results among all datasets and all models obtained from merging non-textual and textual ones. Best result is obtained we merged non-textual with frequency k-grams. So we can say frequency is more informative than just look whether there is a word or not. Among all datasets and all models, NKF gives best result for random forest algorithm, which gives 43.2 PRED 25, 51.49 standard accuracy, and minus 0.37 Gibbs delta. We also built customer-specific models. Our purpose of here is to make specific prediction models for each individual customers. They trained only by their customers' requests. For customer-specific model, we split NKF datasets for each individual customer. We basically picked NKF because it gave best result for unified model, so we decided to use for our customer-specific models. If you look at the figure, RF and random forest and analogy-based estimation give best result as similar result as we obtained unified model. When we compare these models with unified model, we can say there is best solution to predict effort more accurately. Some customers' models are better than unified models, but for some customers, these customers' models worse than this generic unified model. In this work, we have developed an effort estimation system using non-textual features combining with k-grams. Our results shows when hidden information in customer requests are extracted, offers useful features for effort estimation system. Rather than use whether words exist or not, the number of times they have passed in a text has been found to be more important for predicting effort. According to the results in our study, we cannot say whether a customer-specific model or unified model are superior to each other. This may require a more detailed analysis with larger dataset. Our dataset doesn't contain larger effort values too much. Because of that, the models may have learned the lower effort values better than the others. Looking forward, we want to revise our model to include wider effort values. We believe still expert judgment is important. For this reason, we don't want to completely eliminate the expert in our model. For this, we are working on a system where we ask some questions to experts and use the answers given to these questions as features. Thank you for taking the time to listen to me.